Half of my time as a DevRel is answering the same question. What the hell are app-specific rollups? Last time we took a real computer instead of a basic calculation, and we went 3 levels deep on execution environment. But what happens when everyone tries to use different apps on the same computer at the same time? Today we're going 3 levels deep on app-specific rollups and how Cartesi fixes the network congestion and gas fees competition. We will again break it down for a 10-year-old, an engineering student, and a PhD. Let's jump in. Imagine a really busy road where everyone has to share the same 2 lanes. Cars, trucks, buses, all squeezed together. When lots of trucks show up, all the cars slow down, even though the cars didn't do anything wrong. That's what happens on a blockchain. Lots of apps share the same road. And when one app gets really popular, like a big game dropping, everyone else slows down or has to pay more just to get through. Your app might be working perfectly, but it's stuck behind someone else's traffic. Now imagine each app gets its own private lane on that highway. Your app can go as fast as it wants. Someone else being really popular doesn't affect you at all. But Cartesi goes even further than that. Remember the special computer from last video? The one that does the hard maths off to the side? Because your app runs separately, off the shared road entirely, you're not competing for space on it in the first place. You only touch the shared road at the very end, like a cab that changes lanes to drop off the passenger. And because the rest of the time you're choosing to use your own lane, you make your rules for it. You decide the order, you decide who goes first. No one can slow you down, and no one can jump the queue just because they're willing to pay more. Most dApps today run on shared blockchains. Ethereum is the clearest example. Every application, DeFi protocol, NFT marketplace, game, Oracle competes for the same resources. When demand spikes, the gas price goes up for everyone. That's the cost problem. But the deeper problem is the constraint problem. A shared execution environment means one size fits all rules. The EVM wasn't designed for your application specifically. It was designed to be general enough for any application. That compromise shapes everything built on top of it. App-specific rollups take a different approach. Dedicated execution space for your application, custom logic, custom throughput, no competition for block space. But many individuals can validate the app and settle on an existing chain and inherit its security. Cartesi works like this. It moves the computation off-chain. Then you process everything and put the proof on-chain. If a validator disagrees, they raise a challenge. Both parties then run a bisection protocol, a binary search over the execution. They start by looking at the whole execution. Do we agree on the state of step 0? Yes. Do we agree on the state of step n? No. Okay. Let's check the middle. And like that until they identify the first point of disagreement. Then that one instruction is executed on-chain. The chain acts as the arbiter for exactly one computation step. On-chain cost. Big O log n rounds of communication. Big O1 execution. Regardless of how much total computation you run off-chain, it's always this. To build strong DeFi apps, we need to be able to run it off-chain, prove, verify, and even dispute computations. Model the app as a state transition function. Sigma prime is a function of sigma and I, where sigma is the Cartesi machine state, I is the input, and F is the application program running inside the machine. The claim that this transition occurred correctly, that applying I to sigma produces sigma prime, is what gets committed on-chain. The machine state is represented as a Merkle tree over the full RISC V address space. Memory, registers, drives, and device state is what we call a state commitment. The Merkle root is a binding cryptographic commitment to the complete machine state. The state commitments are Merkleized to create a history commitment that represents the trace of the whole computation. There is only one honest history commitment. Validators submit their history commitments on chain, representing their claim of alleged correct execution trace. Duplicates are safely disregarded. These unique history commitments engage in a divide and conquer dispute, engaging in a bracket-style tournament that halves the number of claims each round. Each match in this tournament consists of an interactive binary search. This recurses, halving the search space each round until both parties identify the single step that is disputed. On-chain, a single RISC V instruction execution is verified over the state commitment with the help of Merkle proofs for memory access, like this. Given the previous state of instruction at that step, does executing it produce the correct state? The EVM verifies one RISC V instruction, just one. Total on-chain cost, complexity, it's log n rounds of interactive binary search, where n is the size of the computation. And complexity of the final execution is 1. This is the key scalability property. The cost of dispute resolution is logarithmic in computation size, not linear. Since everything is computed off-chain, computation volume does not translate to on-chain cost. The shared chain is not the execution substrate. It's the settlement and dispute arbitration layer. Therefore, the starvation condition, apps throughput being crowded out by competition application, is absent. Each application's computational throughput is bounded by its own off-chain node capacity, not by any shared resource. No NFTs will interfere with a complex trading platform. That was 3 levels deep on Cartesi's app-specific design. Tell me below which version made the cut for you. Next up, we're going 3 levels deep on DeFi features. Same challenge, same format, different topic. Follow along.